Alright, so welcome to this next class. Any questions on last time? I think we covered a lot of material last time. So last time what we saw was we were trying to draw control structures for this simple process, one reactor, two column process. And we drew an on-demand control structure. We drew a control structure with the reboiler duty in the recycle column, which is the first column, as the throughput manipulator. Now today let's draw a conventional minded control structure for this process. What do I mean by conventional minded? What I mean by conventional minded is okay. I think you guys will have to walk me through drawing of the control structure this time around, so that it's clear to me that at least some things are clear to you. Any other valves? I may have missed some. Okay. So we are putting in A, putting in B. A plus B gives C, C plus B gives D. You are taking out C up the top here, you are taking out D down the bottoms here, and this is AB recycle. Yeah. Now I am going to have my throughput manipulator this way. Okay. So this is going to, the set point, the fresh A feed rate is the throughput manipulator. Okay. Now once the throughput manipulator is set, I can go downstream as well as upstream from there. Upstream there is nothing, or whatever is there is not in my scope. I just have to go downstream now, right? So let's go downstream. How do I manage the fresh B? How do I manage the reactor cooling duty? I would change the reactor duty to do what?
Level.
Huh?
By checking level.
So reactor duty, cooling duty.
Temperature control.
Temperature control, absolutely. Okay, so this is clear. There is a level that needs to be controlled. How will I control it? Well, it has to be this way. The rest of the stuff is actually pretty straightforward. Level control, sufficient reflux so that C doesn't go up the top. Yeah, so I missed a valve here. Yeah. Temperature control so that B doesn't leak out the bottom, because otherwise it will contaminate your product stream. Level control. Level control. Composition control. Well, we discussed this last time. In the absence of any other information, it should be done this way, because the boil up is the larger stream and the bottoms is a leak, and that leak, once the temperature controller is switched off, won't be enough to control the level, right? So we'll do it this way anyway. Okay, how do I manage the fresh B valve? What will I do? I'll maintain it in ratio with the fresh A. So I multiply by the ratio set point, and that ratio set point gives the set point for the B flow controller, right? And how do I fix the ratio set point? To ensure stoichiometric balancing of the fresh feeds. Degrees of freedom, I repeat, 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 things that the operator would specify to run the process. These are the 8 steady state degrees of freedom. Yeah. Conventionally, we are used to looking at a control system that is feed downstream. Okay. What we drew last time was we had the throughput manipulator either at the product stream here or here. Okay. And when we had it here, what we had was the level control was in the reverse direction of flow. When we had the throughput manipulator here, level control downstream was in the direction of process flow and level control upstream was in the reverse direction of process flow. Remember that? Okay. What was this called? This was called the radiation rule. You radiate outwards from the throughput manipulator. Yes or no? Okay. Now, the point is I can choose the throughput manipulator to be anywhere. Okay. Where should I choose it to be? Alright. Now, to understand this, I will give you a very straightforward, simple minded thought process, and based on that thought process you can sort of see. So, let us say I look at again my simple minded tanks in series process. Okay. And it is just a simple tanks in series. All right, you got all these valves. In the absence of any other information, I decided like a simple minded chemical engineer, okay, this will be my throughput manipulator, in which case the level control would be this way. Yeah, we have seen this before, and this is my throughput manipulator. So, if I want to increase the production, the operator would increase the set point of this flow controller, feed to the process. Yes or no? Okay. Now, let us say the economic objective is to maximize production. Why is economic objective maximizing production? Because product is what fetches you money. The more you produce, the more profit you make, the more revenue the plant makes. So, let us say for the sake of convenience that the economic objective for running this process is to maximize throughput production. Okay. Will that always be the case? No. And that whether maximizing production is the objective or not, that depends on the market condition, the demand supply situation in the market. Have you heard of those stories? There was a shortage of tomatoes in the market this year, and tomatoes were selling for, I don't know, 80 rupees a kg. So, every farmer decided, well, it's going to fetch me a premium. So, let me plant tomatoes this year, and next year everybody has planted tomatoes and damn thing has to be sold for and everybody goes bankrupt. You heard these stories, right? So, it may or may not always be necessary, or it may not always be prudent to maximize production, because if you glut the market, then the prices will go down. Do you see? Because the prices are not independent of what you are producing. Okay. But sometimes where there is sufficient demand and there is sufficient shortfall of supply, okay, in those situations producing maximum product is what will give you maximum revenue. Yes or no? But not always. Okay. So therefore my personal view is that somebody should tell me how much to produce. If he tells me produce maximum, I can do that. If he tells me produce this much, I can do that. But if I myself start deciding like those simple minded farmers, tomato, next year everybody has produced tomatoes, everybody goes bankrupt, right. So these economic decisions are best left to the management, who will assess this season is coming, we need to jack up the production of diesel or heating oil because winter season is coming, demand is going to grow, etc., 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 right. I am not a qualified guy, or engineers are not qualified to make those kinds of decisions. They are qualified to produce whatever is to be produced in the most efficient way. That sure they can do, right. But for the sake of understanding, let us say the objective here is to maximize production. Okay. So if you have to maximize production, what would the operator do? Instruction from above is jack up production, produce as much as you can. There is a war coming, produce as much as you can. Okay. Okay, fine. So what is the operator going to do? He is going to keep increasing this set point. Can he keep increasing this set point forever? Yes, no. Okay, why not? Level controller will make sure it doesn't flows. I increase the flow rate, level controller will ensure the outflow also increases.
Temper reaction.
Well, this is just a tank in series, there is no reaction occurring.
The equipment might not be able to handle such.
Absolutely. Can you keep increasing the speed of your car as much as you want? What happens? There is something that gives way. You cannot suck in as much fuel, or you cannot suck in as much air, or something. Okay, some constraint, some capacity constraint will get hit. Yes or no? Now let us say that capacity constraint is this unit 2, some constraint. So there is unit 1, unit 2, unit 3. You are jacking up the throughput. Well, let's see. Okay, let's say the bottleneck unit. This is called the bottleneck unit. As you are trying to jack up your production, unit 3 cannot handle any more feed. Probably because in unit 3 some column became flooded, or some valve became fully open, or some condenser, cooling water cannot be put anymore. There are n number of constraints that you can hit. Okay. So let us say unit 3 is what is my bottleneck. So unit 3 is my bottleneck. Star means, what does star mean? Star means bottleneck. So the operator will increase the throughput set point. Okay. Unit 3 will approach its maximum capacity limit. Okay. If I look at the flows down this train, the feed flow to unit 1 is under flow control. So what do you expect the flow here to be? It will be constant, because the flow controller will not allow the flow to deviate at all. Yes or no? Now in unit 1 there are disturbances that are occurring. Okay, and those disturbances could be of various types, don't want to go into that. So you expect some variability in the flow out from unit 1. Yes or no? Okay. Similarly, there are disturbances that are entering unit 2, okay, which add on to the feed variability to unit 2, and therefore you expect most likely the variability in the outflow from unit 2 would be more than here, right. So stream 1 is the calmest, stream 2 there is some variability, stream 3 there will be still more variability, stream 4 there will be still more variability. Yes or no? Usually this will be the situation. Exceptions are possible, but 90% of the time this is what will happen. Okay. Now unit 3, there is a capacity constraint. What that means is there is a 100% limit. Unit 3 cannot handle if the feed to that unit goes beyond this 100% limit. Okay? Yes or no? What that means is the operator will keep increasing this throughput manipulator set point until what? Until the feed to unit 3 just hits your capacity limit. Yes or no? This is your capacity constraint that you cannot exceed. Yes or no? So this set point of the feed must be adjusted such that whatever is the transient in the feed to the bottleneck unit, that transient, during that transient, the maximum capacity constraint is not violated. Okay, that makes sense? All right. Then what does this represent? The shaded area. This shaded area is lost production. Yes or no? What do I mean by lost production? You see, my bottleneck unit was capable of handling what is the red line, right? But because the flow to the bottleneck unit is deviating and I cannot exceed that red line, I therefore have to be below it, yeah, so that in the transient that my maximum capacity constraint is not violated, right? So the shaded area is actually lost production. Okay. All right. If you want to automate this, right now what is the operator doing? Operator is looking at unit 3, which is the bottleneck unit, seeing the feed to that bottleneck unit, and if he sees that yes, I have approached my maximum constraint closely enough, he stops adjusting, he stops increasing the throughput manipulator, right? I can automate this by saying that look, I am looking at my constraint variable, maybe I will take a whatever is my constraint variable, I will call it active constraint controller. Okay. The job that the operator is doing, a controller can also do. So it is setting the throughput. This is what the operator is doing, right? He is looking at the active constraint. I am far away from the constraint being active, jack up the throughput, right? I am approaching the active constraint value, well, reduce the throughput. Violation is not acceptable, because what that means is then unit 3 will have to be shut down, and if unit 3 has to be shut down or some corrective action has to be taken, that represents a significant economic loss. Okay. All right. So this is what the operator is doing. If I automate it by putting in a controller, do you think this controller will be able to do a good job? How fast would the dynamics of this loop be? If I change the throughput manipulator, unit 1 will respond, it will take its own sweet time to respond. Then the flow to unit 2 will change, unit 2 will take its own sweet time to respond. Finally, the flow to unit 3 will increase, right? There is a large lag. Dynamics is slow. If the dynamics is slow, you can't control too tightly, right? So this is called a long loop. It's a long loop. Because of this long loop is why I am getting so much lost production, because I am not able to control the feed to the bottleneck unit tightly. I would like that control to be as tight as possible so that I can operate as close as possible to my 100%, to my capacity limit. Yeah, but because the feed varies a lot, I can't control it tightly because my loop is a long loop. I have to operate on average at this level My average production is this, whatever, this purple line, and this is actually back off. So, what that means is ever present disturbances or ever present transients oblique disturbances necessitate what? Back off from capacity constraint limit, back off from what? The constraint limit. Is this idea clear? Okay. Now, can I structure my control system differently so that the back off is minimized? Right now I have got a lot of back off, and so if I was capable of producing so many kilomoles per hour, I am actually producing, let us say, minus 5% kilomoles per hour, right. 5% loss in production for a chemical plant can mean millions of dollars of extra revenue, or crores and crores, hundreds of crores of rupees of extra revenue per year. Yeah. So, what should I do? Well, now that I know that the calmest place in my, that my bottleneck unit is unit 3, what I would do is make the feed to that bottleneck unit the throughput manipulator. Yeah, let this be my throughput manipulator. Then level control has to be this way, upstream level controller has to be this way, reverse direction of flow. Yes or no? And now let me look at the flows. This would be the calmest place in my process. Flow here will be constant, and therefore I can jack this flow set point up to be basically at my constraint limit. Red is something that I cannot violate, but since my control is extremely tight, I am operating basically at 100% capacity. Yeah, and then yes, there will be some variability here, there will be more variability here, and there will be some variability here. Okay. Notice that with this orientation of my inventory control system, by choosing the throughput manipulator at the bottleneck feed, what have I done? My flow variability is getting transformed away from the bottleneck. This is a direct consequence of that radiation rule. The orientation of inventory control is transform variability, transform transients in flow away from the bottleneck. What does that do? That allows me to operate at maximum, yeah, and this maximum means significant revenue, right. Even if my production goes up by 3%, 4%, that is a heck of a lot of revenue for the same process. You see, I have not installed any extra equipment, I have not done anything extra or any debottlenecking, etc., etc. For the same process equipment, given that I know that this is my bottleneck unit, this is my capacity constraint, I can orient a control structure by appropriate choice of the throughput manipulator to ensure that back off from that capacity constraint is minimum, negligible, as small as possible. Okay. And that gives me extra revenue benefit, economic benefit. Does that make sense or no? Yeah. So, if my throughput manipulator choice is flexible, if I am free to locate my throughput manipulator anywhere. Okay. Then the throughput manipulator should be located at what? Exactly. So this is I want to write this in. Locate throughput manipulator at process bottleneck. Why do we do it? To minimize the back off, right? So that the deviation from the back off from the constraint limit is as small as possible. Okay. We have already seen, once the location of the throughput manipulator is fixed, the rest of the control system follows automatically. Level control, temperature control, pressure control, etc., etc., etc. Composition control. Yes or no? Okay. However, I do need some extra information. What is that extra information? What is my capacity constraint? Where do I get that extra information from? Operators will tell you, when I try to jack up production, well, my compressor becomes fully open, my compressor duty maxes out, this column starts to flood, etc., etc. Or my reactor temperature reaches its maximum limit, okay, and so on and so forth. You could also do modeling of the process with constraints on temperatures, flows, flooding limits on columns, maximum condenser duty, maximum cooler duty, maximum reboiler duty, etc., etc., and then maximize production. Okay. When you do that optimization, you will have constraints that become active. Okay. That tells you which your bottleneck constraint is. There is, I oversimplified the situation a little bit, not a little bit, actually significantly. When you do this optimization, you will find that it's not usually one constraint that becomes active. It's actually 2, 3, 4, 5 constraints that become active. You see what I am saying? So, for example, if I look at if I look at this process, let us say my objective is to maximize the production of C. Okay. Immediately, as a good engineer, I will tell you, to maximize production of C, what should I do? Well, temperature should be maximum, because then conversion would be maximum. I'm consuming everything, right? Okay. So temperature should be maximum, level should be maximum, level of the reactor should be maximum possible. Agreed with that? Also, this column, the recycle column, should probably be run at flooding, at or near flooding condition. Why? Because that would ensure that my recycle is as much as possible. If recycle is as much as possible, then recycle is mostly A. I want to run the reactor in A rich environment. The richer the more the composition of A, the less the side reaction. Okay. So what that essentially means is, flooding is essentially the boil up, the vapor that's going in the column is not allowing the liquid to flow down. The vapor flow is so much that the liquid is not able to flow down, and therefore your trays get flooded. The liquid just builds up on the trays, it's not able to go down the downcomer because the vapor flow is so high. This is called flooding, right? So flooding is essentially, if a column floods, the first thing you do is reduce the boil up. Once you reduce the boil up, the liquid starts to flow down, finds its way down. Okay. So essentially what that means is, there is a limit on the boil up beyond which you cannot go, because then the liquid is not able to flow down. Does that make sense? Of course, this limit varies with what is the feed to the column and what is the reflux to the column, but nevertheless the basic thing is that it is the vapor that is preventing the liquid from flowing down. Okay, so the vapor must be at a certain limit, it cannot exceed a limit. For the sake of convenience, let us just accept that this vapor limit is fixed. Okay. So then what does it mean? It means that my second column should be run at that boil up. right? That ensures that my recycle is as high as possible. Yes or no? And so on and so forth. So I have already told you 3 constraints that need to be active just by insight. Temperature should be max, because then you will eat up everything, so you can suck in more. I want to jack up production. I want to jack up production in a way so that I keep producing more C than D and not produce too much of junk D which I cannot sell. In fact, I am penalized for selling D. How do I do that? I do that by ensuring that my recycle rate is as high as possible. How do I do that? By running column number 1, recycle column, at maximum boil up or at flooding condition. Yeah. So 1, 2, 3. I keep jacking up the throughput manipulator set point, and let us then say the second column also reaches its flooding condition, because the feed to that column has increased so much. To do the separation, the boil up in that second column also increases, and at that higher boil up, second column also floods. Okay. So my maximum throughput condition corresponds to what? Maximum temperature, maximum level, maximum column 1 in flooding condition, column 2 in flooding condition. Product purity must be maintained. Yes or no? Alright. So the point is, there are multiple active constraints. There's not this thing that, okay, this is the bottleneck unit, this is the constraint that limits production. There are multiple active constraints. How do you handle that situation? Is the question clear? So you want to operate at maximum level, you want to operate at maximum temperature, you want to operate with column 1 flooded, you want to operate with column 2 flooded too, right? So now where do I locate the throughput manipulator? At the reactor, at column 1, at column 2, where? Is the question clear? How would you decide that? So there is not one active constraint, there are 4 or 5 active constraints. Where should I locate my throughput manipulator? Well, that is a question that does not have a very clear answer. It has a clear answer. It is clear to me what I would do. Well, there are these 5 active constraints. If my objective is to maximize production, what I would do is, if I back off 1% from constraint number 1, what is the loss in throughput that I get? This is the sensitivity of throughput to back off in constraint 1. I can get this sensitivity with respect to all constraints, all active constraints. If my column is 1% away from flooding limit, column 1, what is the loss in throughput that I get? What is the loss in throughput that I get if my column 2 is 1% away from bottleneck, away from maximum constraint limit? Yeah. Well, then it is very straightforward. Whichever 9 out of 10 times, what you will find is that of all the active constraint, one constraint actually has a very large sensitivity. What that means is, a 1% back off in this constraint causes a much larger or much more significant loss in production or loss in revenue than the other constraints. Okay. Well, then what does that mean? That means my throughput manipulator should be that dominant constraint. You see, the idea is, if you've got multiple constraints, I would say locate the throughput manipulator at not the process bottleneck, but the dominant active constraint. What do I mean by dominant? What do I mean by dominant? Higher sensitivity.
You know, the most stringent measure is that we have to control the quality or the production of the.
No, we have to, not or, both. No matter what I am producing, quality guaranteed has to be whatever it is that I am assuring the customer. If I am saying my petrol is 87 octane, I am guaranteeing it.
Fine.
Right.
So we'll have a certain production that we have to meet. I mean, let's say 100 kilomoles or 200 kilomoles.
Okay.
So shouldn't our throughput manipulator always be at the back?
No, that's not true. You see, if I look at this, let me try and address it. If I look at this control system, okay, my throughput manipulator is at the feed. Nevertheless, the way I am managing the reflux and the reboil in my product column, if the product quality is deviating, I'll increase the reflux, right? If there is too much benzene that's coming in the product, I'll increase the temperature set point here, right? So, even though my throughput manipulator is at the feed, by adjusting these temperature and compositions, I am ensuring that my product quality is 99 or 99.9 or whatever it is that I want it to be. The point is, this throughput manipulator may be 100, 150, 200. The way I am managing the reflux and the reboil in these two columns, it is guaranteeing me good quality. Your point is well taken. You see, quality is always an active constraint. Just like I am saying, there is a bottleneck constraint, level should be max, temperature should be max, column 1 should be bottleneck, should be at flooding, column 2 should be at flooding. I am saying these are my constraints. Quality is also a constraint, right? And please notice the way I have put in the loops, that is guaranteeing quality is maintained. If you look at the other two control systems that we drew for on demand production or with boil up in the second column as my throughput manipulator, even in that case, the way I put in the loops, it was ensuring that quality is maintained no matter what. Does that make sense or no? Does that answer your question? Okay. So, yeah, that is a good point, in the sense that quality must always be controlled tightly. Okay. You put in those loops, and even then you still have the flexibility of where you want to locate the throughput manipulator. That location you choose for minimizing the loss in either production or loss in revenue or loss in yield maybe, or minimizing energy consumption, whatever may be your criteria. Kg steam produced per kg product. Okay, your criterion may be whatever, throughput, revenue, energy efficiency, etc., etc. Okay, but the point is, no matter what the criterion, there will be multiple active constraints. Okay, and one of them will dominate. Whichever one dominates, that's the one that needs to be most tightly controlled. That's where you locate your throughput manipulator. Do these simple-minded arguments sort of convince you that, look, once I know my economically dominant constraint, control system synthesis or devising a control system for the plant then follows from there. I locate my throughput manipulator there, I put in quality loops for tight control, inventory loops will then follow automatically. Yes or no? Okay. So, now we are sort of getting to a systematic procedure. This mindset can be applied, this thought process can be applied to any process. Yes or no? This is my objective function, energy efficiency for example, or maximizing production or maximizing revenue. To maximize my objective function, what are the constraints that are active? Quality will always be active, plus there will be other things that will be active. Of those other things that are active, which one compromises a back off in which constraint compromises my objective function the most? Locate the throughput manipulator there, rest of the control system follows. Yes or no? So, this is we have done no theory, we have done nothing, we have just gone through a bunch of examples, a procedure has automatically emerged. Yes or no? Okay. So, we can further refine the procedure if you want, but let me just tell you the steps of the procedure that we have gone through. First step was what? Independent control valves. Independent valves. That was the first step. A flow sheet is given to you, you put in independent valves, right? Basically a degree of freedom analysis. What is your steady state degrees of freedom? Yeah. Then what do? You basically either do an optimization, or you at least apply your common sense and figure out, if I want to maximize my production or if I want to minimize my energy consumption, what constraints need to be active. Okay. So, you need to know what are your active constraints for whatever is your economic or production criterion. Okay. So, either from an optimization or from operators will say, well, if you want to maximize production, level should be maximum, temperature should be this column should be flooded, that compressor should be maxed out, etc., etc., etc. Okay. Either an operator tells you this, or you apply your own good engineering sense and figure out this for yourself, or you do an optimization and see what are the constraints that the optimizer tells you must be active. Okay. What I like the most is, what I prefer to do the most is, do an optimization. Optimizer will tell you these are the active constraints. Convince yourself that indeed it makes engineering sense. It does make sense for the reactor level to be max. It does make sense for the temperature of the reactor to be max. It does make sense for this column to be run at flooding. It does make sense for that compressor to be run at max, etc., etc. You see, the optimizer will throw some results at you. You must convince yourself that that does make sense. Okay. Both have to go hand in hand. Otherwise, optimizers, depending on what specification you give, they can actually give very spurious results also, nonsensical results too. You see what I am saying? Okay. So, what are your active constraints? Active constraints for a defined economic objective. What do you mean by economic objective? Economic objective could be revenue, could be production or throughput, it could be dollar energy cost per kg product, could be whatever, or it could be just steam consumption, minimize the steam consumption for the process. Yeah. So, you get those active constraints. Once you have gotten those active constraints, do a sensitivity analysis and in that sensitivity analysis figure out which one is that will give you dominant constraint. Locate TPM at dominant constraint. DC is dominant constraint. Oh well. After that, you just have to synthesize the control system. Yeah. Synthesize the this is a first iteration. I have done a few examples. This is what I have come up with. Okay. This will now be further refined. Okay, because you see, it is not always desirable, or it will not always be that you want to operate your plant at maximum production. Sometimes you may want to operate at half the throughput because there is not enough market demand, right? Boss is telling you jack down the production. We are killing ourselves and the competition by flooding the market, jack down the production. That's what the oil cartel does, right? OPEC, crude's barrel output per day, crude price, well, we need to jack it up, okay, let's reduce the production. Oh, it's increased too much, let's jack up the production. That's what OPEC countries do, right? So there is some interlinking there. Okay, we are talking about production, whatever it may be, max, low, intermediate, high or max, right? So you don't want to operate always at max, you may want to operate at low production rates too with the same plant, and you want to do it in an economically quote unquote optimal way. Yeah, to do that, this simple minded procedure needs further refinement. Okay, that further refinement is probably what we will talk about, maybe through some more examples. Okay, what I would like to do is give you a few examples and then say that, look, this is why it makes sense and this is why this procedure comes out. Just like we have come up with a procedure right now, after doing a few examples, we will do the same, so that your process can be operated using a simple control system, not only at max throughput but also at low throughput, should that be necessary. Okay, that's the next objective. We will do it next time probably. Thank you.